We've spent some time with lesson 6.1 and 6.2 looking at specific properties of exponents and logarithms. So today we're going to use those properties to help us solve. And today we're just going to solve exponential functions. On Monday we will solve logarithmic functions. So we're kind of splitting them into 2 days because they have different properties and different ways that we're going to tackle them. Most importantly, though, the steps that I have listed here is to isolate the exponential function, and we'll see how that looks like in the upcoming examples, if you will. And if it's convenient, we need to make sure that we express both sides with a common base and equate the exponents, which sounds kind of complicated, but it's not. And if we're not able to raise each side to a common base, then we're going to take the natural log of both sides and then use the power rule to help us simplify. So our first example is 2 to the power of 3x is equal to 16 to the power of 1 minus x. So ultimately, they're already isolated by themselves. There's nothing else that we can do at this point. So what I can redo, though, is I can look, you need the pen, I can look at 2 to the power of 3x, but then yet rewrite 16 as 2 to the 4th power, right? Because 2 times 2 times 2 times 2 would be 16. So then they would both have the same base. And then that would be to the power of 1 minus x. Now that our bases are the same, we can utilize the one-to-one property from lesson 6.2 on that very first page at the bottom. I had said we're going to utilize this property when we're solving. As long as the bases are the same, we can say that their exponents must be the same. And then it's got a nice linear equation at this point that we can solve. Remember, when we have a power to a power, we multiply those powers together, which is why I'm taking 4 times 1 minus x. I can simplify my parenthesis by distribution. I can add 4x to both sides, so 7x is equal to 4, and then divide, so x is 4/7 exactly. And if we put that into our calculator, we have about 0.5714. Be careful, because we know My Open Math likes the exact answer, but we also like to double check our work with graphing to make sure that we algebraically did things correctly. So I have the picture on the right-hand side at the bottom. I'm using the Intersect method, which is the method you're probably going to want to utilize for this, where you set one line equal to the left side and one line equal to the right side, and I replaced it exactly as is. And when I did that, I can see that it certainly is intersecting at 0.571 when we take our fraction, our exact fraction of 4/7, and then going ahead and verifying the decimal version, so we can verify that yes, in fact, we did it correctly. We have another example, except this time we have 2,000 is equal to 1,000 times 3 to the power of negative 0.1t. We're going to isolate a little bit here, so we're going to simplify by dividing both sides by 1,000. Therefore, 2 would have to be equal to 3 to the power of negative 0.1t. We have a problem at this point. Our bases are not the same. So we can't follow the same technique that we did for part A. At this point, what we need to do is rewrite them by multiplying both sides by the natural log. So I'm going to multiply both sides by the natural log. Utilizing our power rule, I can bring my power out front so that I have the natural log of 2 is equal to negative 0.1t times the natural log of 3. If our goal is to solve for the variable, I'll want to divide both sides by, I'm going to rewrite 1/10 here. That might make it easier. 1/10 is the same as 1 over 10 here. That's the way I'm going to multiply not only by negative 10 to get rid of my 10 in my denominator, but I'm also going to divide them by the natural log of 3. So I'm going to do this to the both sides so that I have negative 10, the natural log of 2, over the natural log of 3 equal to t. Since 0.1 is the same as 1/10, we can multiply it by its reciprocal to undo that. And at the same time, I would need to divide by the natural log of 3 to undo the natural log itself. Noticing that if this here is going to be a very ugly decimal if we substitute that into our calculator. Specifically, the ugly decimal of about negative 6.309. Again, paying close attention to how my Open Math wants you to insert it. Do they want the exact value or do they want a decimal value? Regardless, I can check utilizing decimals to make sure that at least I did the algebra correctly. I set the left-hand side equal to y so that it's a nice horizontal line. And I set the right-hand side equal to 1,000 times 3 to the power of negative 1/10 t, or x, because decimals likes x. And I can see that, yes, in fact, they intersect at the approximate value that we had found. Let's try another one of those where we have to do a little bit of manipulation on slide 3. Here we have 9 times 3 to the power of x is equal to 7 to the power of 2x. What I can do here is rewrite 9 using 3 squared. So now I'll have 3 squared times 3 to the power of x is equal to 7 to the power of 2x. When we multiply the same bases, remember, one of our rules is that we can add the exponents. So 3 to the power of 2x is equal to 7 to the power of 2x as well. Excuse me, we add our exponents, not multiply them. Oh goodness, that could have ended badly. 2 plus x. All right, but at the same time, our bases are not the same. 7 and 3 are not the same base. So we need to multiply both sides by the natural log. So I'll have the natural log of 3 to the power of 2 plus x is equal to the natural log of 7 to the power of 2x. At this point, we can utilize our power rule to bring down the powers in front of the natural log so that we have 2 plus x times the natural log of 3 is equal to 2x times the natural log of 7. I can go ahead now and distribute the natural log through to my binomial so we can eliminate the parentheses. So 2 times the natural log of 3 plus x times the natural log of 3 equals 2x natural log of 7. 2 times the natural log of 3 is going to be some random number itself. But what I'm going to do is subtract x natural log of 3 from both sides, because within these two terms after I subtract, they both have an x that we can factor out, because ultimately our goal is to solve for this. I'll have 2 times the natural log of 3 equal to x, what we factored out, the greatest common factor, with 2 times the natural log of 7 minus the natural log of 3. At this point, you could probably guesstimate what we're going to do to get x by itself. divide both sides by 2 times the natural log of 7 minus the natural log of 3. So therefore, x is equal to 2 times the natural log of 3 over 2 times the natural log of 7 minus the natural log of 3. So a really ugly decimal is certainly what this is going to be. When we approximate this, plugging into our calculator, we end up with about 0.787. Utilizing the intercept method here, where do they intersect each other? On the left, I wrote it just like I see on my example, where I have 9 times 3 to the power of x is equal to 7 to the power of 2x. Where do they intersect each other? And I can see, yes, in fact, the algebra that we had done earlier matches the approximation from that algebra. Let's move to slide 4. We can try another example. Here we certainly do need to isolate our exponent. To do that, we'll first subtract 30 from both sides. Now we have negative 6e to the negative 0.1x is negative 10. Go ahead and we'll divide both sides by negative 6. So we have e to the negative 0.1x is equal to 5/3. When I now multiply both sides by the natural log, here we go. I need you to remember from lesson 6.2 properties of the natural log. I'm just going to put a little note here. Remember, the natural log is the same thing as saying log base e. And when I have log base e of negative 0.1 to the power of negative 0.1x, these parts undo each other. So then all that we're left with on the left-hand side is negative 0.1x is equal to the natural log of 5/3. I know that negative 0.1x is the same thing as negative 1/10 x. To undo that, we'll multiply both sides by negative 10. So x is equal to negative 10 times the natural log of 5/3 in its exact form, which is approximately negative 5.108. Notice I'm graphing on decimals here to verify, setting the left side equal to the right side. And I do see that they intersect each other at that location. All right. Slide 5. I don't think you can ever have too many examples of these. This time I have my exponent. I have it located in my denominator, so we need to get rid of that. We need to get rid of it in the denominator. To do that, we're going to multiply then both sides by 1 plus 3e to the negative 2t. That in case will eliminate the denominator on the right-hand side. I'll need to distribute 75 to eliminate our parentheses, so that 75 plus 225e to the negative 2t is equal to 100. I now need to get rid of my 75 from both sides, so I'll subtract 75, leaving us with 225e to the negative 2t equal to 25. Still haven't isolated our exponent yet. I need to divide both sides by 225. So e to the negative 2t is equal to 1/9. leaving it as a fraction. Notice I didn't turn it into 0.1 repeated. I'm leaving it as a fraction as its whole value. Now that I have my exponent isolated, I can multiply both sides by the natural log. Recall from the last example that when we had the natural log with e, that they eliminate each other because they're the inverses of one another. So they undo each other. The only thing that would be left would be negative 2t equal to the natural log of 1/9. And then to get rid of our the value with t, we would need to divide both sides by negative 2. So that t would then be equal to negative natural log of 1/9 all over 2, which is approximately 1.099, which does match where they intersect one another when we're using the intersect method on Desmos. Few more examples, because this time I have 25 to the power of x and I have 5 to the power of x plus 6. Bear with me here. I've got two examples that are going to go through the same technique that we're going to do here. We're going to make it look like a quadratic. I'm going to rewrite 25 as 5 squared. And that will still be to the power of x. Now we know that when we have a power to a power, we multiply. So really then this is 5 to the power of 2x. I'm then going to subtract my 5 to the power of x and 6 over so that it's set equal to 0. Notice then that this is quadratic-like. Meaning that I've got power of 2, power of 1, and then no power. So it really is a quadratic in disguise. Let's let u equal 5 to the power of x, the middle term. Then if I were to square both sides, u squared would be the same as 5 to the power of x to the power of 2, or 5 to the power of 2x. Let's replace then 5 to the power of 2x with u squared, and 5 to the power of x with u. Look how nice this looks now. We could find two values that multiply to negative 6 and add to negative 1. Such as negative 3 and 2. So u minus 3, and u plus 2 equals 0. When I solve, then u will equal 3 and u will equal negative 2. U was equal to 5 to the power of x. So 5 to the power of x is equal to 3, and 5 to the power of x is equal to negative 2. To undo that x, we'll multiply both sides by the natural log. We have a problem though. Negative 2 is not in the domain because the domain of natural logs is from 0 to infinity. So if you were to try to put the natural log of negative 2 into your calculator, it's not going to work. It's going to say it's invalid or undefined. So this answer is not a good answer, and we can stop where we are with that one. We can continue solving on the other one because 3 is in the domain, where I can bring my exponent out front so that x times the natural log of 5 is equal to the natural log of 3. And then dividing both sides by the natural log of 5. So that x is equal to the natural log of 3 over the natural log of 5. When we graph, it will be approximately then 0.683. Again, be careful with what My Open Math is asking for. Is it asking for the decimal result, or is it asking for the exact answer, such as that we have here? All right, let's look at number 7. Another one that we're going to utilize that's quadratic-like, so you can see another example of how this happens. We need to isolate our exponents. So to do that, I'll need to multiply both sides by 2 to eliminate the denominator. So e to the power of x minus e to the power of negative x equals 10. This really is e to the power of x minus 1 over e to the positive x to make it a positive value. To get rid of our fraction, we'll need to multiply by the greatest common denominator, which is e to the power of x. When I multiply to eliminate the parenthesis, I'll have e to the power of x times e to the power of x. When we multiply our bases, we add our exponents, so x plus x is 2x. When I multiply e to the x times 1 over e to the x, that will be eliminated. So we'll just have 1 left over. And that will be equal to 10 e to the x. I'm going to subtract 10 e to the x and kind of put it in descending order here. Now we have 2x, 1x, and no x's. So it's set up like a quadratic. Let's let u equal e to the x. So the middle portion. If I square both sides, I'll have e to the x squared, and e to the x squared is the same as e to the 2x, since a power to a power we multiply. Let's use our u's and transform them a little bit. We'll have u squared minus 10u minus 1 is 0. There's nothing I can think of that will multiply to -1 but yet add to -10. So we'll have to utilize the quadratic formula, where a is 1, b is -10, and c is -1. So u is equal to the opposite of -10 plus or minus the square root of -10 squared minus 4 times our a value times our c value, all over 2 times our a value. Simplifying, I'll have positive 10 plus or minus the square root of 100 plus 4 over 2, or 10 plus or minus the square root of 104 over 2. 104 can be simplified into 4 times 26 because we can take the square root of 4. So 10 plus or minus 2 square root 26 over 2. They have a factor of 2 so that I can help eliminate the denominator. So 2 times 5 plus or minus the square root of 26 over 2. Now I have u is equal to 5 plus the square root of 26, and u is equal to 5 minus the square root of 26. Remember we said u was e to the power of x? So e to the power of x equals 5 plus the square root of 26, and e to the power of x is 5 minus the square root of 26. To undo both sides, we'll take the natural log of e to the power of x equals the natural log of 5 plus the square root of 26. And same with our second result. However, the square root of 25 we know is 5. So if I take the square root of 26, that's going to be just slightly more than 5. So if I take 5 minus 5 and a little bit more, this is going to be a negative under here. And you can certainly use your calculator to verify that inside is going to be a negative decimal of some kind. Again, a negative value is not in the domain of the natural log, and therefore we can't find it. It will be undefined, so we don't even need to include this one. I also know that when I take the natural log of e, because the natural log is the same as log base e, they end up canceling one another because they are the inverses of one another. Therefore, x is equal to the natural log of 5 plus the square root of 26, which is in fact 2.312 approximately. So a couple of different ways that you could utilize the quadratics to help us solve a little bit. All right, and the last example, we have a little application problem. The temperature of coffee, T, which is in degrees Fahrenheit, little t minutes after it is served, can be modeled by this function. When will the coffee be warmer than 100 degrees? So we want 100 degrees. I'm looking for when is 70 plus 90 e to the negative 0.1 t. When is this greater than 100? We can go ahead and subtract 100. So I'll have 90 e to the negative 0.1 t minus 30 is greater than 0. So we want to know when is it a positive value. So we need to find where are our critical values so that we can solve the inequality just as we've done in previous units. To find the critical values, we'll want to solve. To solve, I'll have 90 e to the negative 0.1 t equal to 30 by adding 30 to both sides. Divide both sides by 90. When I divide by 90, I have 1/3. Notice I didn't turn this into 0.3 repeated. I'm leaving it as a fraction in its exact value. I also know that 3 could be rewritten as, or 1/3 can be rewritten as 3 to the power of negative 1. To undo this e so that I can solve for the temperature, I'll multiply both sides by the natural log. I know that the natural log is the same as log base e. So when I have the bases that are equivalent together, they end up undoing one another. So negative 0.1 t is equal to, utilizing the power rule here, negative 1 times the natural log of 3. I also know that this is negative 1/10 t equal to negative 1 times the natural log of 3. So to undo, I can multiply both sides by negative 10. So that time is equal to positive 10 times the natural log of 3. We want to know where it's positive. So I've already solved for t itself. We also know, here we go. If I were to put this into a calculator, 10 times the natural log of 3 is our solution itself, is about 10.986. So we can identify values above and below to identify if it is positive or negative. We want greater than. This exactly would give us 100 degrees. Here it's asking, it wants us to be warmer than 100. It doesn't say equal to 100, just warmer than 100. So we're going to exclude this because that's the value that would give us exactly 100 degrees. Also, when I'm thinking about little t is time, would you agree that here that time starts at 0 and goes to infinity? We can't have negative time. So we can have time be 0. We need to check, and we know it has to go this direction at very minimum. So we want to check a value in between 0 and 10 times the natural log of 3, which is about approximately 10.986. So I'll utilize 1. And maybe if I utilize, let's say, 12 over here. When I substitute those values back into our function for t, 1 gives me a positive answer, and 12 would give me a negative result, or undefined. And we're only interested where it's positive. So our coffee will be warmer than 100 degrees from the moment we take it off and it's served up through 10 times the natural log of 3. And I'm going to exclude this because that's when it reaches 100. It's not warmer than 100. It reaches 100. When I graph this, notice that I graphed y equals 100. That's the degree value we were looking for. And then I put the function itself as it's listed. I want to know where is our graph greater than 100? Well, our graph is greater than 100 in this area here, where 0 is included, and this is where it exactly breaks even at the 100 degree value. So this entire interval in between here is where it's greater than 100. And you could pick any marker that you wanted. Maybe you want it greater than 150. So you could have had a horizontal line at 150. The time at which it's going to be warmer than 150 would be a little different, a little shorter interval. Maybe you wanted 75, which is a possibility to look at as well. So a lot of different options that you could have asked questions for this. But this is the last slide. We do have a dedicated slides coming up that are dedicated directly just to solving in lesson 6.5 that we'll tackle next week.